Greetings everyone. I am Uday Sharma from the Triple Department of Institute of Aeronautical Engineering. Today I am going to discuss about the topic the thyristor control series compensation model for power system stability analysis. The thyristor control series compensation or TCSC is a flexible AC transmission system device that is used to improve the power transfer capability and transient stability of the power system. Or TCSC work by injecting a variable series capacitance into the transmission line. This can be used to control the power flow through the line, improve the voltage profile, and damp out oscillations. TCSC consists of series capacitor bank shunted by a thyristor control reactor. The thyristor control reactor allows the series capacitance to be varied continuously, which provides a high degree of control over the power flow and voltage profile. The TCHC model can be represented by a variable capacitor in series with resistor and inductor. The resistance and inductance represent the losses and the thyristor switching time represent respectively. The capacitor respects the variable series capacitance. Here there is a capacitance and two thyristors and there is an inductor. TCSC is connected in series with a transmission line. Thyristor control reactor is connected in parallel with the series capacitor. Thyristors are connected in series with the TCR, that is the thyristor control reactor. The TCSC reactance can be varied by controlling the firing angle of the thyristor. When the firing angle is 90 degrees, the TCSC reactance is capacitive. When the firing angle is 0 degrees, the TCSC reactance is inductive. Between the 0 and 90 degrees, the TCSC reactance is variable. The TCSC model can be used to analyze the dynamic behavior of the thyristor control and its impact on the power system. The model can be also be used to design the test TCSC controllers. TCSC control. The TCSC control. The TCSC is controlled by firing circuit that controls the conduction angle of the thyristors. The firing angle is determined by the TCSC controller, which monitors the power system conditions and adjusts the TCSC reactance to achieve the desired performance. The TCSC controller can be implemented in a variety of ways. One common approach is used to proportional integration derivative or PID controller. The PID controller calculates the error between the desired TCSC reactance and actual TCSC reactance, and the control then calculates a control signal that is used to adjust the firing angle of the thyristor. Suppose there is an inductive error or capacitive error. The TCSC controller or the TCSC model adjusts the firing angle of the thyristors in such a way that the capacitance or inductive error gets minimized or reduced to zero. This can be done here, which is explained by the PID controller. The TCSC can be implemented using more complex algorithms such as artificial intelligence and fuzzy logic or other neural network applications. These algorithms can be used to achieve better performance in certain applications. Here are some factors that TCSC controller typically considers: power flow through the transmission line, voltage profile of the power system, frequency of the power system, oscillations in the power system. The TCSC controller can adjust the TCSC reactance in control any of these factors. For example, if the power flow through the transmission line is too high, the controller can increase the TCSC reactance to reduce the power flow. The voltage profile of the power system is too low, then the controller can decrease the TCSC reactance to increase the voltage. That is, as current increases, the reactance is decreased to limit the current flow. Or the voltage is reduced, the reactance is increased to increase the voltage. The TCSC is a crucial component of the TCSE system. It is responsible for ensuring that the TCSC or thyristor controlled operates safely and effectively. The TCSC model for power system stability analysis. TCSC model for the power system analysis is based on the following equation. That is, TCSC is equals to XC max or C max minus C max X C min multiplied by FU, where the TCSC is the TCSC reactance, XC max is the maximum TCSC capacitance, XC min is the minimum TCSC capacitance, and F of U is a function of TCSC control signal. Here is an under equation where d by dt of XTCSC gives us XC max minus XC min by T of S into F of U minus F of U previous, where the T of S is a sampling time and Fu previous is a function of previous value of the TCSC control unit. Here are some of the steps involved in using the TCSC model for power system stability analysis. Firstly, determine the TCSC parameters such as maximum and minimum TCSC capacitance and the thyristor switching time. Develop a TCSC controller. The TCSC controller can be simply PID controller or any more complex algorithm. Simulate the power system with the TCSC model. The power system can be simulated using a variety of software tools such as MATLAB, Simulink, and the PowerBoard simulator. Analyze the simulation results. The simulation results can be used to assess the impact of the TCSC on the transient stability, oscillatory stability, and the voltage stability of the power system. The TCSC controller for the power system stability analysis. TCSC controller for the power system stability analysis is based on the following equations. Q is equals to Q of P times X reference minus X TCSC plus KD into d by dt of d by dt of X TCSC, that is d square by dt X TCSC, where the U is a TCSC control signal, XP or KP and KD are the proportional and derivational gains, X reference is the TCSC reactance, and X TCSC reactance, desired TCSC reactance. Proportional gain Kp determines the speed at which the controller responds to the errors. The derivative gain Kd determines the amount of damping the controller provides. Thank you. This is Uday Sharma signing off.